An armature provides a stable surface for the clay model to be built on. The design of the armature is important. If it can't support the weight of the clay or stay in a specific shape, then the clay model will fall apart. Let's take a look at the armature from an engineering design perspective. Engineering design is a process that scientists go through to find solutions to problems. The solution often involves designing something, and in this case, that's the armature. The problem that we need to address is what material should we use to design an armature that supports our clay model. The armature has to be made of a flexible material that's water resistant and that can hold at least 500 grams of clay. These are our needs or criteria. Our constraints, or the things that limit our design, are that the material has to be inexpensive and available in the art studio. After doing some research, we decide that 3 materials, wooden sticks, wire, and cardboard, look like promising materials for our armature design. We quickly realize that the wooden sticks are going to be a problem because they're not flexible enough. The piece of cardboard will not work because it loses its strength when it gets wet. The metal wire is flexible and it doesn't lose its strength when it gets wet. But will it hold the weight of the clay? Our next step is to build a prototype using the metal wire. If it doesn't work, then it's back to the drawing board to find another material to test. If the design fails, that's okay. It just means that it needs to be refined and improved upon. And that's how you use engineering design to solve a problem. It's probably something you're already doing. When the artist mixes his dry materials with water to create plaster, a hydration reaction occurs. As the reaction progresses, the plaster begins to harden into a solid. Until this happens, though, the plaster paste acts like a liquid, allowing the artist to spread the plaster over the clay mold. So in general, how is a liquid different from a solid or a gas? Well, when a liquid is in a container, like this glass beaker, it takes the shape of the container, it has a fixed volume, and it flows. The water molecules in this cup are moving around slowly, bumping into each other and the sides of the cup. We can't see this happening because the water molecules are too tiny. But imagine these ping pong balls are the water molecules moving around inside the cup. They're bouncing off the sides of the container, but they're staying fairly close together. A gas, like this steam, has molecules that are spread apart and in constant motion. They're hitting the sides of the container, and some of them are escaping out the top of the container because air pressure isn't able to hold them in. A gas does not take the shape of its container, it does not have a fixed volume, and it flows easily. Now let's look at a solid, like this ice cube. It does not take the shape of its container, it has a fixed volume, and it does not flow. The molecules in the ice are vibrating in place, close together, and staying in a fairly specific shape. Solid ice does not flow because its molecules can't move over and around each other. So once the plaster hardens into a solid, the artist can take away the aluminum dividers and not worry about his plaster flowing or dripping onto the floor. Water does not mix with waxes and oils, a fact that the artist takes advantage of when he separates his wax copy from the plaster mold. Living things take advantage of this too. This magnolia leaf has a waxy covering on its surface called a cuticle. See how the water beads up on the leaf? The waxy barrier helps keep water inside the leaf, where it's used for photosynthesis. Apples have a coating of natural wax as well. The waxy coating helps the apple stay firm and juicy, and it also acts as a barrier to keep bacteria and certain fungi out of the apple. Certain penguins make a special oil that they coat their feathers with when they're preening. This oil makes their feathers virtually waterproof. So why don't waxes and oils mix with water? Well, water is what we call a polar molecule. It has slightly positive and slightly negative charges on it. This causes water molecules to be attracted to each other and stick together. We call this cohesion. It's what makes the water bead up on the magnolia leaf. Oils and waxes are nonpolar molecules. They don't have any charges on them. This clear plastic bottle contains colored water, which is polar, and mineral oil, which is nonpolar. You can see that the two do not mix and that the oil does not dissolve in the water. So that separation helps the wax come loose from the plaster mold. The artist added tube-like structures called SPRUES to his design to make sure that the molten metal is distributed evenly throughout the mold and to allow any trapped gases to escape. That's important. Gases have some unique properties that make them, well, a problem if they're trapped inside a closed container and heated. When a gas is trapped in a closed container, its molecules bounce around, hitting the sides of the container. If that gas is heated, then the energy that's added to the system causes the gas molecules to move around even more quickly. As those gas molecules ping around off the sides of the container, they create pressure on the container. So, as the movement of the molecules increases due to the increase in temperature, the pressure they exert on the container increases as well. If we were to graph it, it would look like this. Let me show you how this works in real terms. I'm going to take this empty soda can and place it on this hot plate. The top of the can is open, so any gases can escape at this point. Right now, the pressure outside the can is equal to the pressure inside the can. Next to this, I have an ice water bath. In a second, I'm going to take this can that's filled with hot gas off the hot plate and flip it upside down in the water bath. The water will seal any hot gases inside the can, and that gas will experience a sudden decrease in temperature. So the temperature of the gas trapped inside the can decreased in the ice water bath. This caused the pressure inside the can to decrease as well. So the pressure outside the can was now higher than the pressure inside the can, making it collapse inward. It's dangerous to heat up a gas in a closed container because in that instance, the change in pressure would be such that the can could explode outward. Imagine that there weren't any SPRUES or ways for the gases to escape our mold at the foundry. As you can imagine, if those gases were exposed to extreme heat, that could cause a big problem with the sculpture. Gravity is the artist's best friend when he's pouring the molten bronze into the mold. As the bronze leaves the crucible, it flows down into the mold and fills it from the bottom up. Gravity is the force that causes the molten bronze to flow downward. It's the force of attraction that exists between any two masses. In this case, the mass of the bronze is attracted to the far larger mass of the earth. Let's see how this works with something that's not quite so hot. I've poked a hole in the side of this cup and I'm going to fill it with water. I'm covering the hole with my finger. What will happen when I move my finger away from the hole? The force of gravity will cause the water to flow out of the hole toward the floor. Now, same setup. But this time, I'm going to drop the cup and uncover the hole at the same time. What do you think will happen? In this case, gravity is acting on both the water and the cup at the same time, so you don't see the water flow out until it hits the table. Areas of the bronze that have not been covered with a protective coating will tarnish over time. Tarnishing is a chemical change in which the bronze reacts with oxygen in the air, becoming darker over time. Placing a layer of wax or oil between the metal and the oxygen in the air can prevent this from happening. Let's take a look at these pieces of steel wool. Steel reacts with oxygen in the air to form rust over time. This piece of steel wool was spritzed with water and then allowed to dry in this uncovered dish. Over time, it reacted with the oxygen in the air, forming rust. This piece of steel wool was treated in the same way. The only difference is that I coated this piece of steel wool with mineral oil. As you can see, no rust formed. The mineral oil formed a barrier between the metal and the oxygen in the air. Bronze pieces can also become discolored when they come in contact with certain acids. Bronze pieces that are displayed outdoors can be exposed to acidic rain, acidic pollutants in the air, and even uric acid, which is found in bird droppings. This kind of damage isn't unique to bronze statues, however. Marble statues are also at risk of being damaged by acids in the environment. Take a look at these marble chips. They're made out of calcium carbonate. When these marble chips are exposed to an acid, like this hydrochloric acid, they start to fizz or bubble. This is an indication that a chemical reaction is occurring that's causing the marble chips to be broken down into carbon dioxide gas, calcium chloride, and water. Chemical changes like these cannot be reversed. That's why they're of great concern in art conservation.